All right, so now we're going to take a look at how we can apply what we've learned about gases to chemical equations. And as we've seen before, when we looked at chemical equations, the most important thing that you're posed with in a chemical equation is the fact that it's balanced. And we can use that balanced equation to determine the number or the amount of any reactant or product by using those coefficients, which are your mole to mole ratios from that balanced equation. So it's really going to be important, as with any chemical equation, that it's balanced first of all, and then we can use that mole to mole factor or those mole to mole factors to solve any problem. And that includes equations or reactions that have gases in them. So just as a preview, in order to use that balanced equation, we would need to get to moles of a gas. And then we can use that balanced equation. So the best law to use, the best gas law to use that has moles in it would be the ideal gas law. Once we use that, we can get a number of moles of the gas, then the whole equation opens up. We can solve for moles and then consequently amount of anything else in that balanced equation. Let's take a look at an example of how we can use gas laws, specifically the ideal gas law, in a chemical equation. So here we have an equation that represents the reaction between limestone, which is just calcium carbonate, CaCO3, reacting with hydrochloric acid, HCl, to produce carbon dioxide gas. We get some liquid water, and then we also get aqueous calcium chloride. So you'll notice here our equation is balanced. We have the coefficient of 2 that balances that equation. So then we're asked how many liters of CO2. All right, so this is what we're interested in, the carbon dioxide. We need the volume of CO2 in liters are produced, and then we're given some conditions, right? So we're asked how many liters of CO2 are produced, and then we're given the pressure, right? So you have to recognize mmHg as millimeters of mercury, and that is a unit of pressure. So let's write that down. We have 752 millimeters of mercury. We're also given temperature as 24 degrees Celsius, and if you remember from all your gas laws, you want to make sure that your temperature is in Kelvin. All right, so we need to add 273 to that, and you want to convert that right away. Don't wait, because I guarantee you are going to forget to convert it. So that gives us 297 Kelvin. And then we are told that we have a 25-gram sample of limestone. So we have the mass of the CaCO3 calcium carbonate as 25.0 grams. All right, so those are everything we were given. Now, again, because the equation gives us a mole to mole ratio, we can use the amount of calcium carbonate. Okay, so we're going to use the amount of CaCO3. Okay, so we're given that we have 25.0 grams of calcium carbonate. Now remember, the equation, it doesn't give you a mass to mass ratio, it gives you a mole to mole ratio. So in order to use that equation, right, where we're given the amount of calcium carbonate, we want to relate that to the carbon dioxide, the CO2. We would need to first of all get the moles. We have to get to moles of calcium carbonate. All right, so you want to convert this to moles of CaCO3, and that's something you've done before in the chemical reactions chapter. All right, so let's just do that right away. We have 25.0 grams of calcium carbonate, and then to get from grams to moles, right, we used a molar mass of CaCO3. Okay, so we can calculate that. We have 1 calcium, we have 1 carbon, and we have 3 oxygen. So 1 mole of CaCO3, we add those together, give us 100.09 grams for the molar mass of CaCO3. So the grams go away, we end up with moles of calcium carbonate. So if you calculate that, all right, so we divide 25 divided by 100.09, and that's going to give us 0.249. So we round to 3 sig figs, that's going to give us 0.250 moles of CaCO3. So now, once we get to moles of calcium carbonate, we can use the mole to mole ratio from that balanced equation. All right, and that tells us that 1 mole of, from the balanced equation, okay, 1 mole of calcium carbonate produces 1 mole of carbon dioxide. So I can use that equality as a conversion factor. All right, so from my previous step, I have my 0.250 moles of CaCO3 that I calculated from the mass. Then I'm going to take my equality here that I get from the balanced equation and stick that in as a conversion factor. It says that 1 mole, and I put the calcium carbonate underneath because I wanted to cancel, produces 1 mole of CO2. All right, and obviously here, that's going to give us 0.250 moles of carbon dioxide. That's our gas. Okay, so we get the moles of carbon dioxide. What we needed to find here is the volume of CO2, right? Well, we know that we have the pressure P, we have the temperature T. Okay, we just calculated here the number of moles, that's N. Okay, so we have P, V, and N. What we need to, PT and N. What we need to calculate is the volume V. All right, so we have the majority of those variables, so we can use the ideal gas law, which, remember, PV equals N times R times T. We need the volume, okay, which is V. So we need to solve this for V. Okay, so in order to isolate V on one side, we do a little bit of algebra on this. All right, so we move P over on the other side. We need to put it underneath. In other words, we divide both sides by P, and then we end up with, well, let's just do that. Divide both sides by pressure. So we end up with PV, it's nRT. We divide both sides by P. P cancels here, and then we end up with volume is equal to N times RT divided by the pressure. All right, so we just calculated N, the number of moles of the gas. That's N here. R is the gas constant, which doesn't change. Okay, that's 0.0821 liter times atmosphere per mole Kelvin. Those are the units. Okay, our temperature, we just calculated that at the beginning to be 297 Kelvin. And then the pressure we were given as, that in millimeters of mercury as 752 millimeters of mercury. All right, so with any calculations you do, you want to make sure you have the right units. So 752 millimeters of mercury in our ideal gas constant, the pressure is actually given in atmospheres. All right, so we need to convert this to atmospheres. All right, so we use the relationship between atmospheres and millimeters of mercury. For every 1 atm, that's defined as 760 millimeters of mercury. That goes away. All right, so we end up just dividing now the 752 divided by 760, and that's going to give us 0.989 atmospheres, ATM. So we have all of the numbers that we need now to solve for V. Okay, so we substitute those. Into our equation. So then our volume is equal to N, our number of moles, which we calculated as 0.250, times the ideal gas constant, 0.0821 liter atmosphere per mole Kelvin, times the temperature, 297 Kelvin, divided by the pressure, which we just calculated as 0.989 atmospheres. So if we look at our units, all right, moles cancel here, Kelvin cancels there, and atmospheres cancel up there. So the only unit we're left with now is liters, and that's great because that's what we wanted to find. So our units tell us that our manipulation, our algebra, our math, etc. is correct. All we need to do then would be to plug these into your calculator and evaluate what V is going to be. So using your calculator, you plug those numbers in, and you should end up with 6.16 liters of carbon dioxide. All right, so here what we're seeing is there are a couple things actually that we are putting together. So we just learned in this chapter all about gases, and specifically we learned about several gas laws. Really the best one, or the one that's all-encompassing, is the ideal gas law. So we were able to use that ideal gas law to solve for volume in this case. What allowed us to use that is our balanced chemical equation that we had at the beginning. All right, so just to recap here, we were given the amount of the calcium carbonate in grams. We needed to figure out the volume of the CO2. The way that we did that was we first of all converted the mass of the calcium carbonate into moles using the molar mass. Then we used the mole to mole ratio between the calcium carbonate and the carbon dioxide to get to the moles of CO2. Then we used all the other things that we were given, and we plugged that into our ideal gas equation to solve for the volume V of the gas in this case, which was our carbon dioxide.